identify 7 different kinds of damage. Give a sense of how many therapies might need to be created to address the category relatively comprehensively.
Right, excellent question. So I'm going to be repeating the questions because for the recording. So the question was, we've got 7 categories of damage, but within each category there are going to be various examples. So what are we actually looking at in terms of the number of therapies that are going to have to be applied to each individual at the same time in order to achieve comprehensive rejuvenation? And it's going to be quite a lot. I think we're definitely talking about dozens of different things done at the same time. Could be even more than that. Because, for example, with cell loss, pretty much what we have to do is stem cell therapy, but there's a lot of different types of stem cell therapy for different organs, and we're going to have to do a lot of those things. The reason why stem cell therapy is such a big field is because one has to look at the details of each organ in order to get it to work. But the reason it's a field at all, of course, is because, you know, different stem cell therapies do have a lot in common as well. I think it's important to emphasize that the reason why this particular classification is a useful classification is because of that. It's because we can describe within each category a therapy which, with only relatively minor variations, will work with each example within the category. Go ahead.
How do you explain the fact that evolution hasn't already cracked this?
So the question is, why do we still have aging, since evolution could, in principle, surely have dealt with it? And this is, again, a very important question that people have put a lot of thought into over the years. The thinking actually goes back to the 19th century. A famous German biologist named August Weismann, in the 1880s, not long after evolution was invented, started thinking about exactly this question. He said, well, okay, surely evolution would have got rid of aging if it were such a bad thing, so it must be a good thing. And he came up with a very nice parsimonious theory for why it's a good thing, essentially that it improves the signal-to-noise ratio of natural selection by allowing competition between young individuals of a species to happen more easily without the interference of the old individuals. And that idea was accepted extremely uncritically for about 70 years, not least because August Weismann was terribly famous and important, and therefore he must be right. But then in the 1950s, an English biologist named Peter Medawar said, hang on, there's a rather fundamental thing that breaks this theory entirely, which is that in the wild, there's an enormous amount of death from causes that don't have to do with how long ago you were born. And that means that there's hardly any individuals out there that are old enough to exhibit any actual physiological decline, which means that there's no substrate on which natural selection can actually act to create, or indeed to maintain, the genes encoding some kind of deliberate aging. So people since then have completely accepted, almost everybody completely accepted that actually aging is not a product of evolutionary intent, but rather a product of evolutionary neglect. That's the way that one of my colleagues, Len Hayflick, put it. But then we have to ask, okay, if it's not a good thing, where did the neglect come from? And the answer is, evolution doesn't care very much. Medawar was actually slightly oversimplifying. You have to have a bit of death from aging, or else aging will speed up over evolutionary time. Because the reason why we live as long as we do is because we've got an awful lot of inbuilt automatic anti-aging machinery, maintenance machinery that works without our medical intervention. And therefore the only question is, why isn't that machinery perfect? Why doesn't that machinery fix all the damage that metabolism creates? The answer is simply, there are too many types of damage, and they accumulate at a wide variety of different rates. So some of them accumulate rapidly, and those are the ones some of them would accumulate rapidly if there were not a defense mechanism against them, and therefore there has to be a defense mechanism evolving, or else we won't have any offspring, so we'll be gone. But some of them accumulate so slowly that evolution doesn't care, because we've had our offspring beforehand, and evolution, of course, only cares about survival of the genes rather than survival of the individuals. Next. Go ahead.
How do you reply to critics who say that this type of research will result in a severe problem with overpopulation.
So the question is, how do I respond to people who worry about the consequences of this research? The predominant one being, well, certainly this is the most common complaint, that we might end up with a dramatic reduction in the death rate and thereby a dramatic rate of increase of global population. And since we have a problem with global population already, etc., etc. That's, of course, only one of the many things that people say about the social consequences and psychological and personal consequences. They say, won't dictators live forever, and how will we pay the pensions, and won't it be boring, and so on. There are two types of answers that I like to give to all of these questions. The first answers I like to give are specific to the actual question, the actual individual concern. So in the case of overpopulation, I point out, number one, we've got already a rapidly declining rate of fertility, average number of kids that a woman has, that in every single case, without exception, occurs in any society in which women become educated and emancipated. And that's continuing still, even in the Western world. Number two, that not only are women having fewer children, they're also having them later, presumably because there's other things they want to do with their life before they do this terribly time-consuming thing. And one thing we're going to be fixing with all of this is menopause. So women are going to be able to have their kids later and later and later and later. And that will have an enormous impact on the trajectory of global population, even though it's not normally taken into account when fertility rates are discussed. Another thing that we have to take into account is the impact of technology on the carrying capacity of the planet. If we invent nuclear fusion 20 years from now, for example, and we get to work properly and efficiently so that we end up using far less in terms of fossil fuels, then lo and behold, suddenly you can afford to have a lot more people on the planet. There's not really a problem with having 7 billion people. The problem is there's 7 billion people burning a lot of fossil fuels, and so on. So you can make all these specific arguments, okay? And that's all very well. But of course these specific arguments are speculative by definition, because we're talking about the relatively distant future. So someone may say, well, yes, you may be right, but you may be wrong, mightn't you? And I say, absolutely, I might be right and I might be wrong. And that actually gives, comes to the second answer, which applies, again, across the board to whatever objection you may put forward. I'm certain that this uncertainty about the future imposes an absolutely clear moral obligation on us to develop these technologies as soon as possible. Because the absolutely clear thing that we do not want to have happen is that we today say to ourselves, oh dear, there's this particular problem that's going to happen if we were to invent this technology, and humanity won't be very happy, therefore let's not invent the technology. And then, 30 or whatever years from now, humanity of the future finds out that we were wrong, and the prospective problem does not exist, so they'd like the technology, but they don't have it because we couldn't be bothered to develop it. We do not want to be in a position of having condemned a whole cohort of people to an early death, an unnecessarily painful death, just because we thought we could predict the future. Yeah?
Is it possible that we have exponential increases in costs required to do research proposing that prevents us from ever reaching the escape velocity?
Right, so the question is, will the rate of progress that the required rate of progress that I described earlier as longevity escape velocity be frustrated by the increasing cost of developing increasingly sophisticated medicines? I think that the risk of that possibility is vanishingly low, essentially because I don't expect that as we move forward into addressing more and more difficult types of damage, we will identify significant new categories of damage. I think that what we'll identify is increasing numbers of examples within the existing categories. And as I mentioned in response to the first question, within a category, you're talking about small, relatively modest variations on the previous, on pre-existing therapies. So, since there are relatively modest variations on pre-existing therapies, it's really hard to imagine how it could cost a great deal to develop them, or indeed to disseminate them. Yeah?
What would you account for, like, a certain lack of progress in terms of these paradigm shifts or understanding clearly amyloid processes have been studied for decades now in terms of the pathogenesis of Alzheimer's, and there's many therapies that actually can wipe out the amyloid accumulation, yet there's still Alzheimer's disease. Likewise, in terms of cancer, there's been tremendous amounts of money poured into cancer research, yet there's still cancer. So
Okay, so this is a rather general question. How can we explain why progress has been so slow despite the allocation of really large amounts of money to these various problems?
I mean, if these damage categories are
Right, yeah. My essential answer to your question is that the overwhelming majority of the money that's been spent on the attempt to develop effective medicines against age-related diseases has been in the attempt to develop things that fit within what I call the geriatrics approach to combating aging. In other words, they constitute attempts to address the diseases, the pathologies of old age directly, rather than to address their causes. What I'm proposing here is an approach that we could, in 2 words, simply call preventative geriatrics. And preventative medicine in general is really rather a Cinderella of medicine. It's not something that gets a lot of money for its development. And that's hardly surprising because it's also rather a Cinderella in terms of public attitudes. The public sort of intuitively know that medicine is basically black magic, and therefore they're not very happy about actually submitting to medical attention while they're still healthy, because they think, the cost-benefit ratio isn't too good. But ultimately that's what we're going to have to do. We're going to have to educate people to understand that these therapies, even though they are to be applied before someone exhibits clear disease, are essential for postponing the age at which that person would actually get that disease. I think that it remains absolutely essential to continue development of what we can think of as the geriatrics approach, directly attacking these diseases, because when applied in conjunction with preventative geriatrics, they'll be much more effective. We'll be able to take people who are not simply in middle age, but are actually suffering from the diseases and disabilities of old age, and we will be able to pull them back increasingly from the brink by, first of all, addressing the diseases, and second of all, ensuring that the therapies that address the diseases do not suffer from this downward spiral of accumulating damage, because we're fixing the damage as well. Any more? Hello.
You identified 7 things that cause damage, and those are the things you're concerned about addressing. But could there be an 8th thing that hasn't been found yet that could be less attractive?
So the question is, could there be an 8th type of damage? And I gave a couple of reasons why I don't think there's an 8th type of damage. First of all, that it's been a few decades since we found the 7th, and secondly, because if we describe where damage can accumulate, that tells us a good deal about what type of damage can accumulate, and we can just drill down and describe what the body's made of, and come up with this sort of list. However, both of those arguments can be viewed as not completely cast iron. So I don't think that there is a 0 chance of our coming up with an 8th type of damage. Then again, but how do we find it? Perhaps the only way we will find it, if it hasn't been found so far, is by going and fixing the ones we do know about, and thereby unmasking the 8th one. And we'll worry about it when we find it. Yep.
The machines you showed that go beyond the normal age eventually do break down. There's sort of a time period. It's not going to go infinitely. What you're describing here for life is almost infinite.
So what's the problem with my... Your question is, what's the problem with my analogy?
Yes.
Okay, so yeah, the question is, so the
Second related question. I'm sure you're familiar with the MacArthur work on this. They kind of define the life of cells to be 120 years.
All right, I'll come back to that one.
You're going way, way beyond.
All right, all right, all right. So there's two separate questions here. So the first question is, if we look at simple man-made machines, yes, we may be able to extend their lifespan beyond normal, but they still fall apart eventually. Well, I would like to challenge that. If we take the example of the Land Rover, then yes, it's built well, but what that gives it is a long warranty period. You know, it's expected to last 50 years, and it will indeed go downhill eventually, in the same way that the human body goes downhill eventually, even though it goes downhill only after a lot longer than it takes for a dog's body to go downhill. However, if we take the case of maintenance as a manner of extending the lifespan of machines, then I don't agree with you. We don't just have 50-year-old cars out there, we've definitely got 100-year-old cars out there, and they just don't have a mortality rate. We don't have 200-year-old cars, but that's not because we don't know how. It's because cars hadn't been invented 200 years ago. So, you know, it seems that at this point, longevity escape velocity for cars is already negligible. You know, we're not having to work any harder on 100-year-old cars to keep them going than we were working on the same cars, let's say 30 or 40 years ago, when they were only 3 or 4 times older than they were designed to be. So I don't agree with you. I think that maintenance we have fine concrete examples of maintenance actually giving indefinite lifespans. Now, the other question that you had was with regard to a specific aspect of aging, namely the division of cells and the type of aging that results from the division of cells. And this is an area that's very hot at the moment because there is a lot of good science happening in this area. But the good science is not really undermining, in fact it's not remotely undermining, what we already know about what cell division means for aging. 50 years ago this year, actually, 1961, Len Hayflick published the remarkable discovery, as it was thought to be then, that if you took fibroblasts from the lower layer of the skin, the dermis, and you asked them to divide and divide and divide, then eventually they just wouldn't divide anymore, after about 50 divisions. And everyone thought that this was terribly exciting, and a lot of people, essentially as a result of Len's choice of terminology, he called it cell senescence, a lot of people presumed that this had something to do with aging of individuals. But it doesn't. Or at least it doesn't have anything like such an obvious link with aging of individuals as Hayflick and others thought. Because these cells in the lower layer of the skin normally don't divide very much. They divide like crazy when they're in a wound, and that's what they're there for, really. But normally when they're just in a stable environment, they just hang out. So your average fibroblast doesn't need to divide as often as 50 times in a normal lifetime. So, of course, it doesn't need to be equipped to do so. There are some cells which do need to divide a lot more often than that in a normal lifetime, especially the stem cells of certain rapidly renewing tissues, such as the upper layer of the skin, the epidermis, or the blood, or the gut. But those cells do have a mechanism for escaping the Hayflick limit. They express this famous enzyme called telomerase, which compensates for the DNA modifications, this shortening of the ends of the chromosomes that happens when a cell divides in the absence of telomerase. Fibroblasts from the lower layer of the skin don't express that enzyme because they don't need to, and because it turns out to be convenient as an anti-cancer mechanism for cells to avoid expressing any more of this enzyme than they can avoid. You can see that it's an anti-cancer mechanism because cancer is a disease of indefinite and uncontrolled cell division. So if the act of cell dividing causes the cell to become less able to divide in the future, that's a good anti-cancer defense. So that's the essential answer to your question. It's not clear that there's a significant role for this process of cell senescence in actual organismal aging. It probably does play a role in the immune system, but it may very well not play a role anywhere else. At the back.
Do you have any thoughts about what might be a natural sort of upper bound on age limit due to non-age-related diseases? So if people live longer, they're reproducing less, there's the potential for more virulent pathogens.
Mm-hmm.
So people contracting various diseases that way. And is there some thought about
Right, so the question is, what is there any kind of inherent limit on how long people can live if aging doesn't exist as a result of causes of death that do not have to do with aging? Now, the simplistic answer is, well, obviously not, because if aging is not a feature of risk of death, in other words, if your risk of death in the coming year is not dependent on how long ago you were born, then it's just radioactive decay, which clearly means that some people can last indefinitely. Actually, it's a good deal better than that, because the longer you live, the longer you have to benefit from the advances in technology that reduce the risk of death from causes other than aging, as well as aging itself. So in fact there is good reason to believe that the estimate I gave of 1,000 years there is actually an extremely conservative estimate. So you mentioned pandemics as a potential reason why we might have some kind of limit. That's just one example. You know, once we don't have aging anymore, or I think actually once we even get to the point of anticipating that we will quite soon not have aging anymore, we will be putting a hell of a lot more money into vaccine development. Vaccine development is a very poorly funded area of the medical industry, basically because it's not very profitable. But once infectious diseases start to be a major cause, a cause of a major proportion of deaths in the Western world again, same as they used to be, then I think that's going to concentrate our minds quite significantly. Yeah, Daniel.
I've been following you for a long time, and I've been wondering, if we weren't going to age anymore, what age would we be? I'm curious, what age would we hang out at a longevity escape velocity? Right,
so the good thing about, so the question here is, what age would we choose to be? What biological age would we choose to be if we could get to longevity escape velocity? And I think the important thing to remember about this is that these therapies, since they are rejuvenation therapies, which do not affect the rate of creation of damage, allow us to oscillate in our biological age. In other words, if we take these therapies very frequently and very thoroughly, then we will be biologically 20 or 25. If we take them less thoroughly, less frequently, then maybe between 35 and 50 or something like that. But the point is we can change our minds. We don't have to do the same thing until we get hit by a truck. We can do whatever we like. So it's a moving target that we can change at our will.
What would be a lower bound when we stop growing this?
So what would be a lower bound on one's biological age? I would say more or less 20, because this is not going to in any way reverse the process of development to adulthood. It's only going to reverse the accumulation of damage. Of course, the term biological age in the context of medical intervention is always a little bit of an approximation of the truth. In practice, if we repaired damage 100% well, then we would have a biological age in terms of damage of 0, or actually minus 9 months, but we would have a physiological age in terms of our body plan and so on of maybe 20. Yeah?
In healthy humans who are 90 and have 10 years more of pretty good health before they're really frail, at the cellular level, is there any evidence that their 10 years of reserve in a 90-year-old is sort of like, I don't know, a diabetic who's not doing great shape, doesn't have frank braking, but has all this cross-linked protein and a lot of that sort of problems of accelerated aging, who has 10 years to go? I'm just sort of pushing at whether you have some evidence of a kind of metric of just a few dimensions of this damage as an intermediate in the causing of age-related mortality.
Okay, so the question is, do we have a good measure of these types of damage as effectively biomarkers of how long the person is likely to live in the absence of any therapies that we might invent in the future? That's the question, right? Yeah?
Well done.
Okay, so people have been looking for biomarkers of aging that are reliable for an awfully long time, and it's been an extremely futile and frustrating quest. Essentially, the problem is that there are so many things that one can end up dying of eventually, in terms of the final proximate cause of death, that any individual predictor of that will be only a predictor of one or maybe a few types of causes of death, and you may be caught by the other ones first. So the essential answer is that one would intrinsically need quite a complex biomarker, a quite complex composite biomarker in order to be predictive, and we're just not there yet. However, the good news is we don't really need to know how biologically old someone is in order to decide what to do. One thing that we can take into account is the fact that the rate of accumulation of various types of damage in the body doesn't vary all that much from one person to another. And we know that just by looking at longevity. So I mentioned that the world record lifespan is 122. Now, very few people die of age-related causes below the age of 60, right? So this sort of tells us that we've got the option of just not diagnosing people at all, just not bothering to measure their biological age, just giving them therapies at a sufficient rate that would work for pretty much everybody. And that does mean that we're going to be giving some people some therapies twice as often as necessary, but that's probably going to be the lesser of the two evils. Yep?
Are there simplistic biological organisms that would be suitable guinea pigs that tend to fail from one or maybe two of the 7 deadly sins or whatever?
Yeah.
I forget.
Yeah. So the question is, are there other organisms we could study that would help us to characterize and develop treatments for the individual components of this grand plan? And the answer is more or less no. Whenever you study a simpler organism, you're studying an organism whose metabolism is very different, and therefore the details of what damage they accumulate, even though they may fit into more or less some of these categories, is very different indeed. And so the therapies you develop don't necessarily translate, even if you actually look at mice, which are obviously mammals and fairly close to us. There are always going to be profound differences, just the same way as there are for drug development today for any other cause. However, the good news is that a slight variation of your question has the opposite answer, has the affirmative answer. The variation is, rather than looking at other species, what we do is look at sick people. People who have some genetic predisposition or perhaps some other predisposition that causes them to get some particular type of damage much more quickly than most people do, but not to accelerate the accumulation of other types of damage. People like that are perfect for experimenting on the efficacy of a therapy for each particular type of damage, and I'm fairly sure that they will be exactly how these therapies are actually rolled out. Right, what's it now? 10 to 9, I suppose we better stop. I'm happy to hang out for a bit longer outside, so long as there's a bit more wine. Thank you all again.